So awesome. Thank you for the kind introduction. Super excited to tell you a little bit more about how we think about generative AI and simulation at Torque. So I came to Torque about a year ago with the merger of Algolux, and Algolux was a startup that I kicked off during my PhD with a focus on end-to-end imaging and perception. So at Torque, we're thinking this story a little bit further, and we're building autonomous trucks with Daimler Truck under the Freightliner brand in the US here. And so Torque hasn't really been all too public about their technology in the past, and I've been wanting to change that, and we did that recently in a number of talks. So before I go into the meat of the presentation on our learned simulation stack, let me start by going over our AV stack. So we built an AV stack that you can roughly imagine as the stack that I'm showing you here in the top, separated into modules that perform perception, prediction, and planning. And the interesting thing is that learning is really used in all stages of this particular pipeline. So this is a modular stack with parameters of the models being learnable independently of them being neural networks or being conventional algorithms. And we make this possible by making the stack itself differentiable. So specifically through the introduction of differentiable proxies or differentiable modules that allow us to then bring some of these traditional modules, post-processing operators, in some cases also pre-processing ingest operators that you have in your overall stack into a differentiable form or fashion. And this allows us then to, independently of the algorithmic choice, backpropagate gradients all the way from the end to the individual modules. So I want to make this a little bit more concrete and just pick out one particular module. So here I'm picking out our multimodal BEV stack, which performs perception in the bird's eye view. And so we rely on a multimodal model that fuses information from different sensor sources, raw data directly from cameras, from LiDAR sensors, and from radar sensors. And we use raw data in a different way than, for example, you might be used from the Tesla stack. And in fact, directly include the ISP in the model that we train then in an end-to-end differentiable stack. So we kind of extend here even the stack and backpropagate some of the gradients all the way outside of these post-image modules to something that happens even before data is present in image form. And so that's an interesting aspect that I'd like to highlight on end-to-end training. So here's an example of a proxy pipeline with a differentiable proxy for the image processing pipeline itself. And then using these proxies, we're able to optimize for precision and recall as an intermediate metric here, even all the way down to the ISP. And what you see here are the images being optimized in this process. And you in fact get images that are not pleasing to a human, but are optimized for computer vision here in this particular case, all driven by downstream loss. So one really interesting example of where end-to-end training and optimization can help you quite significantly. So we extend this to a full BEV stack where we use a wide baseline stereo stack that performs stereo depth to place our features in BEV space. And this functions up to 1,000 meters, which is essential because we have high resolution cameras, that's possible, but we absolutely need it for long-term planning tasks. And to really make this work, object detection isn't really the only thing that you have to solve in the stack. And again, coming back to the end-to-end message, we need to extract other things as well. In particular, pose and calibration is super important. So in the bottom, I'm showing you an illustration of the white baseline stereo stack here. And this is a prototype vehicle that has this vertical bar here where the cameras are mounted on both sides of the bar. So in the wild, typical AV stacks require constant recalibration, oftentimes every single time at the hub, where we have to account for calibration changes. Actually, during a drive, there can be very severe vibration. So in a trucking application, you can quickly get out of calibration and end up with a scenario that I'm showing you here on the left side, where you have an issue because of vibration, you lose calibration, and then your stereo stack can't really perform anymore well. So again, as another example of a learned end-to-end stack, we can actually optimize along with the stereo correlation, so extracting features, pulling them in a stereo correlation volume, also the calibration information, the pose that we use here. And that works really well if you do it end-to-end. So another example is then what this enables us is to solve tasks as the one that I'm showing you here. On the right side, I'm showing you a dense example of ultra small objects, lost cargo that we have to detect up to 200 meters at ultra long ranges in order to perform safe maneuvering on highways. And here, these high-resolution cameras, so almost double-digit pixel, double-digit megapixel cameras, allow us to detect these small objects at long distances with 8 million points in real time. So in the prediction and planning stack, just to complete the stack, we also rely on a fully learned prediction and planning stack. And this is essential to allow us for plans that take ambiguity into account. So our learned planners run alongside the conventional analytic planners that form safety constraints. And then in an EBM style fashion, we make sure that we don't go out of those constraints, but can at the same time navigate within multiple futures. So what do I mean by multiple futures? So let's look at this example here. Here we're predicting the modes of multiple future trajectories of the agents that I'm showing you here. So here in blue is the past trajectory, and then in purple is the predicted one. And we're predicting multiple different ones here. So here's a left yield scenario, a potential collision that we also predict, which is absolutely essential for the rest of the stack, the planner, in order to make a good decision, as well as a right yield situation. And we do this as a sets of sets approach where we use a transformer-based method with one set of agents per time step, and then we unroll the sets of sets into several time steps over time that we can then use to have a full social behavior prediction. So the agents react to each other and they react over time. From there, we take this one step further and include a learned scene context in the prediction and planning stack. And so notably, future predictions will be used in all planning stages, both in short-term and long-term planning. So using these multiple futures are learned parallelized on agents that are aware of each other through this differentiable prediction and planning framework. And the key thing that I want to get across is that end-to-end training does not only benefit these stages, but really benefits the entire stack, tracking persistency, occlusions, other parts in your stack that you have. So that was a quick overview of the stack that we have been building, which hopefully provides a little bit more context of the meat of my talk, which I'm going to talk about now. So the key thing that we need in order to train this entire stack and perform end-to-end learning is data from the start, so from the sensors themselves, all the way to the end. And we need diverse data, and we need it at scale. So for the remainder of the talk, I'll describe our world simulator context that allows us to generate this data at scale without relying on massive annotation. So to bring training and validation data together, we use high-quality generated data, such as both from neural rendering as well as generation. So here's a few examples where we generate at large-scale data that we have only seen through a few different drives that we then aggregate and in a neural rendering approach retarget. And you've seen perhaps a lot of work at a few of the scientific conferences where we presented some cool approach that really scaled this to full routes. And the cool thing that you can then do is you can come up with completely novel scenes, right? That's effectively what we want to do. We want to create counterfactual scenarios, want to drive vehicles that we haven't seen along different trajectories. We want to change our own trajectory. We want to maybe change even our own sensor set. And this is all hinging on work in my lab. I'm leading an academic lab at Princeton as well, that we really brought to a very large scale at Torque here to make our stack work. The interesting thing is that if you mix that with layout conditioned models, such as the one that I'm showing you here, we can create completely new scenarios that are multi-view consistent and temporally consistent. I'm showing you here our own conditional model with some diverse scenes that we never capture, but use for training and validation in our stack. So then you get these pixel accurate annotations, of course, but you also get the temporally consistent outputs of the video models that we use for training and validation. And creating these videos and training data at scale is one thing that's exciting, but there's actually another key aspect in this as well that I'm super excited about, and that's opportunities for explainable vision using inverse rendering. So I'm showing you here a few examples of these generative models that do something completely different. So instead of generating data just for training and validation, what we do here is we generate data in a test time, zero shot manner, where we optimize an image, these scenes that I'm showing you here, that closely matches the actual image that we have observed. So we basically fit the scene, or imagine the scene that best fits the image that we actually observed. And it turns out that this approach of thinking about tracking here in this particular case generalizes ultra well. So in fact, all of the tracking results that I'm showing you here are done on data that the model has never seen. So these are completely unseen examples that the method has to deal with. And so just on a high level, the way how it works is that we look at this as a re-identification problem, where we solve tracking or matching as inverse rendering. So let's say we have two particular frames. We have detections for a given time step for, let's say, from an off-the-shelf 3D detector. Then given this set of detection, we generate pixel regions with your favorite generator, be that either a diffusion model or a different approach. Let's say even potential GANs work that we have tried out. You fit those, and then we train that generator on large synthetic data. So only rendering engine outputs. But then by simply just backpropagating the pixel loss all the way from the downstream losses, we're able to optimize in latent spaces because we trained a generator here to generate us pixel regions with shape latents and texture latents. And we're able to optimize. So this was all a lot of architecture overview. So if you have an input frame as such, and we get a really bad initial detection here. So these are overlaid detections with gamma corrected image inputs that are not matching well with an average per class latent showing you here for the individual classes. Then if you only optimize the texture latents using a perception loss, this already works well because we use synthetic data, purely rendered data to train our model. Right? So this is one of the generalization benefits of this particular approach. So uniform texture matches, in fact, very well. Next, if we add pose, this does already better, and we can recover from pretty bad poses. And if we then finally add shape, this completes our optimization approach. And all done just simply by using backpropagation. And while this was an extremely bad example, if you have temporal data, you perform tracking over time, you can improve your latents, you can improve your poses, and you get much, much better performance. So that's, in the end, why this particular approach here worked well and did perform, as I'm showing you here, on completely unseen data super, super well. So train it on Waymo, test it on new scenes, for example, works super well as an ultra-effective prior. This concludes some of the perception data, how we think about generating perception data at scale. But I haven't really talked about behaviors. And behaviors is really the key thing for our AV stack. So to evaluate behaviors in an AV stack, typical simulation stack, if you go to applied, in the industry involve replaying logs, right, with slight modifications. So you start from an existing captured scenario and you modify this scenario by varying these replays slightly to generate more diverse scenarios. But they're generally not closed loop, and it's challenging to generate diverse scenarios from offline data. So completely counterfactual scenarios, for example, a crash or an adversarial behavior that an actor might do is something that you don't oftentimes see. And our approach to tackle this problem at scale is offline RL. So this is something that we very recently found works extremely well and allows us to tackle this problem at ultra large scales. So we focus specifically on controlling agents, so to alter a real driving behavior into a wide range of different agent behaviors, including both bad and good driving behavior. So let me illustrate that a little bit. So let's say if you have this nominal behavior that I'm showing you here on the right side, a lane change, where the blue is the agent that we control and the pink is our AV planner, where here the blue agent was just simply following the traffic flow. So this is what we observed in our data set. Then what we can do is we can generate an adversarial behavior and actually have this agent speed up. But we don't want to do this in a manually crafted way where we generate lots of scenarios, use for telex, and then come up with many, many more manually crafted approaches. How do we automate this? And that's where return condition reinforcement learning really solves a big gap for us. If we combine it with what we call exponential tilting. So let's consider this traffic scenario that I'm illustrating here on the right side, just two vehicles passing each other. And then if we can implement certain levels of control, so vehicle-to-vehicle tilting, which is one approach where we optimize or tilt the distance of the two vehicles to each other, the vehicles that we want to control, and we will later see that we control whatever vehicles we want. Vehicle-to-edge tilting, so we can control the distance of the vehicle to the edge of the map, the road edge, and we can control the goals, so we can make our vehicles not reflect their goal-finding behavior anymore. And so in order to make this work, the first step is to come up with a good data set. So we use our own data as well as other data and pipe this through a physics-grounded engine, because this is perception output data. So we don't necessarily know if it's consistent with the underlying driving physics. And then given this data set, we are modeling this thing here. So we're modeling basically a factorization of the joint distribution of multi-agent scenes. We model states, actions, and factorized returns. With this particular factorization, which has the future state prediction, return policy, and return prediction. And that's going to be important in order to tilt it and modify the behavior. And then at test time, we can simply tilt the sampling of the individual return components for the specific desired behavior. So for these individual three knobs that I showed you at the very beginning. And this then makes our return condition policy conditioned on the tilted value to generate a controllable scenario. Model functions as follow. So we have an initial scene encoding using a transformer encoder that performs cross-attention between the individual agents that we have of the map of our data set and the map itself. Then during training, decoding starts by embedding each of such agent states, actions, and returns at every time step. And then this is kind of similar to a traditional language modeling embedding layer. And then for every agent at every time step, we then auto-regressively decode the agent's return component following the next action it should take. And this requires a really complicated temporal masking strategy that really makes all of this work. So we make sure that the agent only looks at its own states when generating its future states and doesn't have privileged information such as the other agent states or most likely actions. Works. Then at inference time, we auto-regressively decode with the states of all agents given. And then the state predicts the return to go, and the return to go predicts the action, and the action predicts the next states. And we can just tilt the goal with this exponential tilting approach, and can sort of think of this as modifying the goal behavior then according to our factorization that we came up with in the first place. Here's a few examples that show you some of this qualitatively for multi-agent behaviors. So let's say if I'm having a tilted scenario in the top middle, so there was no tilting. Now, here's a negative tilting example where I'm showing you a crash scenario, and on the right side is a yield scenario where I very conservatively yield with my adversarial or other vehicle that I'm looking at. Yeah, I'm having some video issue, but the key message I want to get across is that this is a controllable stack. So one advantage of this approach of exponential tilting is that we can smoothly control the specific agent's behaviors. We're showing you three controllable behaviors. So again, vehicle-to-vehicle collision, vehicle-to-edge road collision, and goal achievement. And once we smoothly increase the respective tilting value, the metric of interest here, collision rate, off-road rate, or goal success smoothly changes, as I'm showing you here in these qualitative plots. So yeah, having a video issue here, so I'll not be able to play those. Oh, this one here plays. So this is a lane change scenario. That's an interesting one, where the nominal scenario was not a change at all. So these two vehicles were just following each other. Yeah, it does not play. Like the adversarial behavior causes a crash in this particular case, and actually learns to change lanes accordingly. So, in conclusion, I can give you also an offline view of some of the videos. We can fully simulate agents in the scene choose to only simulate a few agents that can comfortably react to each other, and all agents are aware of each other and can interact with each other. This is our approach to generate very large set of particular behaviors. If you're interested in knowing more about Torque, please ping me in with that. I'd like to thank you all.
Much. We have time for a couple of questions. Anybody have questions? Yes.
Thank you for the talk. That was very interesting. I was thinking, when you were talking about the masking that you do after the embedding, you said it's a bit complicated. How do you, at that step, I assume, deal with kind of respecting causality? Because you said some of the states are not accessible. That's right, that's cool. But at the same time, there are states that should be the next one you look at. So.
Yeah, exactly. So the masking is exactly how we designed that, right? So that our agent only knows its own past, but doesn't have access to the other agent's reward states, right? So yes, it can observe the other states, but it cannot know the other goals, right? So the policies of the other agents, because we learn policies effectively for every individual agent, can only be known by the agents that I'm controlling at the moment.
Okay, understood. Thank you.
Yeah.
And sorry about the videos.
In terms of the figuring out which scenarios to simulate, are you doing just like a naive simulation where you just generate a bunch of situations and you're like, okay, let's just try it out on all these? Or do you have a stack rank where you prioritize, these are the scenarios where we've seen some edge cases or where we think the consequence could be like more deadly than others?
Yeah, it's a really great question. So a lot of this is motivated really by the availability of data. So we simply don't have many crash scenarios. Even if you buy all of the truck crash scenarios on our pilot roads, it's just 100 crashes from Dallas to Laredo, right? So you can't train a model here. So that's the scarcity of the data that we have to deal with, right? So, but going one step further, so we actually train our model then on the data that we generate, test it again, right, and generate additional examples, additional adversarials that are as adversarial to our own planner. So this is a cool thing. You can actually use this also as a planner that's very aggressive, for example, and can be tilted towards positive and negative behavior.
Thanks so much for the talk, Jeremy Welland. I had a question around my past. I've been in human safety and looking at data there. I'm wondering if you talk to actual drivers that give you batshit crazy examples, because it's such a low set of actual crashes and deaths, but probably a greater set of near misses. So do you learn from that at all?
Yeah, so we actually, it's a really great question. So we actually look at these crash reports, right, which are police reports where folks hypothesize we don't have any tracks, no additional information other than an hypothesis what may have caused the crash. And there's very interesting scenarios, right, including a lot of lost cargo scenarios. So we have a lot of lost cargo scenarios, and we have observed only a few. For example, a pipe could hit a truck and potentially, if things got worse, pierce even the fuel reservoir, right? So things like that can happen, and you have to account for them, right? Yeah. But what we really have an issue with in terms of data availability are the long tail scenarios, the crash scenarios, the aggressive actors, the adversarial actors that follow and tailgate. So there's just not a lot of data. And so that's why we need a scalable approach that doesn't require on scenarios, because scenarios also will not scale for us.